طيب يعني عزيزم كاتتان باش بابتي أو رومان بريتيلا chapter 2 لا introduction to nuclear physics the journal Science nuclear energy. Today's subject is chapter 2 titled nuclear energy in the subject of introduction to nuclear physics. Nuclear binding energy. The nuclear binding energy is the energy required to break a nucleus into protons and neutrons. So a system of separated nucleons has a greater mass than a system of bound nucleus. Here in this graph, this is a nucleons or a nucleus, which is plus a binding energy, the amount of energy to break up the neutrons and protons and separate them. It will become like this graph. These are separated protons and neutrons or separated nucleons. So it has been proved experimentally that when the protons and neutrons are separated, the mass will be greater than when the neutrons and protons are stuck together. Binding energy, we will call it BE. The difference between the computed mass in equation 1.1 in lecture 1 and the real mass is the mass defect. So delta M equal to ZMP plus NMN minus M3, which was equation 1.3, where M is the measured mass of the nucleus. From Einstein's energy equation, E equal to mc squared, thus binding energy B equal to delta mc squared. So binding energy equal to ZMP plus NMN minus M multiplied by C squared. The nuclear binding energy may be expressed in atomic mass unit if we divide equation 1.8 by C squared and express the masses in AMU. So binding energy in the units of AMU equal to ZMP plus NMN minus M. We also find that often the nuclear binding energy is expressed in terms of millions electron volts, MeV, or mega electron volt, MeV. The conversion factor is 1 atomic mass unit equal to 931.5 MeV, mega electron volt. Binding energy per nucleon, BEN, in nuclear physics, one of the most important experimental quantities is the binding energy per nucleon, BEN, which is defined as the average energy required to remove an individual nucleon from a nucleus. If the binding energy per nucleon is relatively large, the nucleus is relatively stable. A graph of binding energy per nucleon, various atomic number, a total number of nucleons is given in figure below. This graph is considered to be one of the most important graphs in nuclear physics. The graph rises at low A, peaks very near iron, Fe, and then disappears off at high value of A. So the binding energy per nucleon, the peak value suggests that the iron nucleus, Fe, is the most stable nucleus in nature. The reason the graph rises and tapers off has to do with competing forces in the nucleus. At low value of A, attractive nuclear force between nucleons dominate over repulsive electrostatic force between protons. But at high value of A, repulsive electrostatic force between forces begin to dominate. And these forces tend to break apart the nucleus. So the binding energy per nucleon, various A graph implies that nuclei divided or combined release a large amount of energy. This is the basis for a wide range of phenomena, from the production of electricity at a nuclear power plant to sunlight. Example. Find the binding energy of oxygen, 16 nucleus. The mass defect delta M equal to mass of Z proton and N neutrons minus mass of the nucleus, and the binding energy delta M C squared. So delta M equal to mass of 8 hydrogen atoms plus mass of 8 neutrons minus mass of neutral oxygen atom. If you put the numerical values, the result EB equal to 127.8 MeV. What is the average binding energy per nucleon? Binding energy per nucleon, EB, equal to EB divided by number of nucleons. So the above result will be divided by the number of nucleons, which is 16. The result will be 7.986 mega electron volt per nucleon. Here is the graph we mentioned. It can be seen that the graph starts from the lowest value of A, which is 2 of hydrogen, and then rises, and then goes to lithium second, beryllium, boron, helium, nitrogen, iron, freon, neon, chlor, and iron. So the peak is here. This is the peak. It's about something about between 60 to 70, and then the toppers or the disappears, the graph goes down. This is the most important graph in nuclear physics, which shows average binding energy per nucleon in mega electron volt as a function of mass number or the number of nucleons in the nucleus, number of nucleons in the nucleus. Example 3. What is the binding energy of deuterium? The deuterium nucleus H12 has 1 proton and 1 neutron. So the binding energy equal to mH plus mn minus md, where mH mass of a proton equal to 1.007825 atomic mass unit, and mn mass of a neutron equal to 1.008665, and md is a mass of the nucleus of deuterium. So mH plus mn equal to 2.01649 AMU, and MD equal to 2.01410 AMU. So the binding energy is the difference. It comes out to be 2.224 mega electron volt. Per nucleon, it will divide by 2. It will be 0.112 MeV per nucleon. Example 4. What is the binding energy of the most common helium nucleus? Helium nucleus has 2 protons and 2 neutrons. So binding energy equal to 2mH plus 2mn minus mHe. 2mH is equal to 2.01565 AMU. 2 neutrons will be 2.01733 AMU. And the sum will be 4.03298 AMU. And mass of helium, nucleus helium, 4.002603 AMU. And the difference will be the binding energy equal to 28.3 mega electron volt. Per nucleon equal to 7.07 MeV per nucleon. The binding energy per nucleon is many orders of magnitude greater than the binding energy of the electron in the atom. You may notice that the binding energy per nucleon is greater for helium than for deuterium because the atomic number is more. Semi-empirical mass formula, SEMF. The binding energy is usually plotted as B divided by A, binding energy divided by A, or binding energy per nucleon. This illustrates that the binding energy is proportional to A. The dependence of B over A on A and Z is found by the semi-empirical mass formula. This formula is based on first principle consideration and on experimental evidence to find the exact parameters defining it. In this model, the so-called liquid drop model, all nucleons are uniformly distributed inside the nucleus and are bound together by the nuclear force. The Coulomb interaction force causes repulsion among protons. Characteristics of the nuclear force and of the Coulomb interaction force explain part of the semi-empirical mass formula. The semi-empirical mass formula, SEMF, is MZA equal to Z MH1 hydrogen plus NMN neutron minus BZA, or BZA divided by C squared. This is the semi-empirical mass formula. So in the semi-empirical mass formula, we have 5 parts. The first one is the volume part, then the surface part, and then the Coulomb force part, and then asymmetry part, and then the pairing part. in this way. So the semi-empirical mass formula EB equal to AVA minus ASA to the power 2 by 3 minus AA, A minus 2Z squared less A divided by A to the power 1/3 minus AC Z multiplied by Z minus 1 less A to the power 1/3 plus delta AZ. This is the volume term, and this is the surface term, and this is the asymmetry term, and this is the column term, and this is the parent term. So semi-empirical mass formula consists of 5 terms. For pairing term, delta, the coefficient of the will be delta AZ equal to plus delta 0 when A and Z are even numbers, and it will be equal to 0 when A odd number, and equal to minus delta 0 when AZ are odd numbers, and delta 0 equal to AP divided by square root of A. And these are the value of the coefficients given here in numerical in mega electron volt for semi-empirical mass formula. So semi-empirical mass formula sometimes is called Bethe and Wiesacker formula. It is, as I said, 5 terms: volume term, surface term, column term, asymmetry term, and parent term. This is a very important formula ever been found in nuclear physics. The student must know and understand it very well. Pairing term, as we said, it will be pairing term will be positive when even, and will be negative odd, and will be 0 when even and even odd. We will now study each term in the semi-empirical mass formula. A volume term. The first term is the volume term, AVA, that describes how the binding energy mostly proportional to A. Why is that so? Remember that the binding energy is a measure of the interaction among nucleus. Since nucleons are closely packed in the nucleus and the nuclear force have very short range, each nucleon ends up interacting only with a few numbers. This means that independently of the total number of nucleons, each one of them contribute in the same way. Thus, the force is not proportional to this value. The constant of proportionality is fitting parameter that's found experimentally to be AV 15.5 megaelectron volt. This value is smaller than the binding energy of the nucleons to their neighbors. It is found that the energy binding energy of one nucleon to the other nucleons is on the order of 15 megaelectron volt. The total binding energy is the difference between the interaction of a nucleon to its neighbor and the kinetic energy of the nucleon itself. Surface term, also based on the strong force, is a correction to the volume term. The volume term rising from the fact that each nucleon interacts with a constant number of nucleons independent of A. The nucleons on the surface of the nucleus have fewer nearest neighbors. This term is similar to surface force that arise since the volume force is proportional to BV, which is proportional to A. We expect the surface force to be proportional to V to the power 2 by 3, since the surface is equal to volume 2 by 3. Also, the term must be subtracted from the volume term, and we expect the coefficient to have a similar order of magnitude as AV. So AS is about 13 to 15 megaelectron volt. Column term, the third term, derives from the column interaction force and protons and is proportional to Z. The term is subtracted from the volume term since the column repulsion makes a nucleus containing many protons more energetic. To motivate the form of the term and estimate the coefficient AC, the nucleus is modeled as a uniformly charged sphere. Symmetry term. The column theorem indicates that it would be favorable to have less protons in a nucleus and more neutrons. However, this is not the case, and we have to invoke something beyond the liquid drop model in order to explain the fact that we have roughly the same number of neutrons and protons in a stable nuclei. There's a correction theorem in the semi-empirical mass formula which tries to take into account the symmetry in protons and neutrons. This correction can only be explained by a more complex model of the nucleus, the shell model. If we were to add more neutrons, they will have to be more energetics, thus increasing the total energy of the nucleus. This increase more than offset the Coulombian repulsion, so that it is more favorable to have an approximately equal number of protons and neutrons, I minus z minus 2z squared. It can be easily understood by considering the fact that this term A goes to 0 for A equal to 2z, and it is effectively smaller for larger A. The coefficient of asymmetry term, A asymmetry, is 23 mega electron volt. Pairing term, the final term is linked to the physical evidence that like nucleons tend to pair off. It means that the binding energy is greater, thus the delta is positive, if you have an even nucleus, where all the neutrons and all the protons are paired off. If you have a nucleus with both an odd number of neutrons and of protons, it is less favorable to convert one of the protons into a neutron or vice versa. Thus, with all other factor constant, we have to subtract delta, which is negative, a term from the binding energy for odd configurations. Finally, for even odd configuration, we do not expect any influence from this pairing energy, so delta will be zero for even odd configuration. Thank you very much. I wish you success, and I hope that today's lecture will be useful for you. Thank you.